Okay, electrophilic addition mechanism. So the reactions of alkenes, which we learn are addition reactions, where things add and the double bond goes away, are all electrophilic addition reactions, which means that the species that adds to the alkene can be considered an electrophile. An electrophile being something that is electron deficient and therefore likes electrons, if you think of what that word means. So the double bond, it acts sort of like the opposite. It's the area that's electron rich because we have two pairs of electrons in that bond. And if you recall, the second bond between the two carbon atoms, the first bond, or we say the first bond, but one of the bonds is a sigma bond, and the second bond is a pi bond. And so that pi bond comes from those parallel p orbitals, and it's above and below, that's all one bond, above and below the axis where the two atoms are bonding between the two nuclei, and therefore it's a bit more, it's a bit further outside of the two nuclei, so it's a bit more out in the environment, and it's a more reactive area of electron density. So that's why the pi bond is going to be the thing that goes after or is donated to the electrophile. And so when we draw our curly arrows in this mechanism, they're going to originate at the double bond, because that's the area where you have an electron pair that can be donated. So two of the addition reactions have mechanisms that you need to be able to draw, and that's for the bromination and the halogenation. So for the bromination mechanism, and I'll start with just ethene, since it's our simplest alkene. Now, it might seem strange, why is bromine an electrophile? Both bromine atoms have an octet of electrons, so it wouldn't necessarily jump out at you as an obvious electrophile. And the concept is that as a bromine molecule gets closer to the double bond and the pi bond of the alkene, that actually induces a dipole in the bromine molecule. And so this side of the molecule gets a little bit negative, and the side closest to the alkene gets a little bit positive. Because again, if you think about, there's actually sort of a area of electron density here and here. And so when the bromine molecule gets close, it sort of pushes or repels away the electrons within the bromine, and it polarizes it. So it induces a polarity in the bromine molecule. That's why the bromine molecule ends up being attacked by this pi bond. So I'm going to take away those little bits. We don't need to draw those parts. Okay, so in the mechanism, you need to show the curly arrow originating at the double bond, one of the bonds, and going towards the bromine. Now, in the bromine itself, in organic, we don't actually need to show those extra dots. So we can just do that. Okay, now we know from seeing nucleophilic substitution and such that if this arrow is coming in to form a new covalent bond, that bromine is unlikely to form an extra covalent bond. So actually, it's going to cause this bond to break, which means that those two electrons are going to leave with the other bromine. That's the Br molecule splitting apart. So that's our first step. And if we think of what we have now, this carbon still has two H's attached to it. And I'm going to pick the left-hand carbon to be forming the bond to bromine. I have to pick one of them. And this molecule, it doesn't matter which one I pick because it's an entirely symmetric alkene. So there's the first bromine, the one that had the electrons donated to it. So this has now formed a bond. So the double bond of electrons is now this pair of electrons that's between the carbon and the bromine. If I keep going, I've now got this carbon with its two H's, and I've got the Br minus that kicked off from the bromine molecule. So it should look odd to you. It should look like that carbon on the right is sort of missing something. That's because it is. It's now positively charged. It's now a carbocation. So this is a carbocation intermediate. So now there's a positive charge on that carbon atom. We can also put this in brackets and indicate the positive charge there if we'd like, but the positive charge is sort of focused on that carbon atom. Now, you may be able to predict what's going to happen if you've got a positive carbon atom right there that's sort of open, missing one of its bonds, and you've got a bromide ion over here with a negative charge. It's probably not too hard to imagine that the negative will be attracted to the positive, and that will be the second step of the mechanism. So I'm actually going to erase it from here. So that was our first step. And then in a distinct second step, we've got the carbocation, and we need to show the curly arrow coming from a lone pair on the bromide ion going towards that carbocation. So when we're done with this mechanism, we've now added a bromine to each carbon atom, and we've got our dibromoalkane from bromination. Okay, so this is the mechanism. It is a two-step mechanism, and it does have a carbocation intermediate. So in that way, it's a lot like the SN1 mechanism. The difference from this and SN1, well, one is substitution, one's addition. So when we end with this one, everything has been combined and added together into one final product instead of there being something that gets kicked off. There's also an extra arrow in the addition mechanism. So you notice there's 2 arrows in the first step, and there's then a third arrow in the second step. So there's 3 arrows total, whereas the substitution mechanisms only have 2 arrows total. There is some evidence for this mechanism, meaning that it takes place in the steps like this. It's a bit off topic. I don't really think it's relevant for the IB exam, but if you carry out this mechanism in the presence of chloride ions, so you do your alkene, C2H4 is our ethene, plus Br2, and if you just have some Cl minuses in there, you actually get a mixture of these two things. So this is the product that we made in our mechanism, but you also get some of that. So you get a mixture. Now, why is that evidence for this mechanism? Well, it's evidence that there is a point in this mechanism where a carbocation is formed, because and that the bromine has to add on first. So meaning in the first step, you've got the donation to the first Br, and that this first bond is formed. That's sort of the first step of the process, and then you're left with this intermediate that has a carbon atom that's positively charged. Because you could perhaps imagine that if you have Cl minus ions sort of lying in wait in your solution, then when you get to this point, after the first step, the Cl could just as easily attack that positive carbocation carbon as the bromide ion. And so as a result, you get 2 different products because each of those negative ions can go after that positive carbon, and it's about a 50-50 chance for them to do that. But both products here have this first Br attached, so that sort of is evidence that the first bromine attaches first in a first step of the mechanism, and then the Cl minus and the Br minus could both attack in the next step. So it gives evidence to the fact that it's a 2-step mechanism, and that the second halogen doesn't add until the second step. But I really don't think that is very relevant for the IB. So I'm going to take this off of our official notes here, and I'm going to end this video now. So the mechanism for electrophilic addition involves 3 arrows, always starting at the double bond, breaking apart the halogen, forming a carbocation intermediate, and then the halogen ion attacks the carbocation to add the second halogen.